Hi everyone. So today we are going to learn a new problem or perpendicular axis theorem. This problem is in continuation with the previous one that we have learned, the concept of parallel axis theorem. Both the parallel axis theorem and the perpendicular axis theorem are very important for all the Olympiad exams, all the entrance exams and all the physics exams. By this problem, we are going to learn how to apply the perpendicular axis theorem and parallel axis theorem in a single problem. So let's start. So first we are going to learn about the perpendicular axis theorem. The perpendicular axis theorem is applicable for the planar object. Means this is only applicable for the 2D bodies, two-dimensional bodies. It states that the moment of inertia about an axis perpendicular to the plane of an object is sum of the moment of inertia about two perpendicular axes that lie in the plane of the object and intersect at a point. So formula is given that it is Iz is equal to Ix plus Iy, where Iz is the moment of inertia of about the perpendicular axis, that is z-axis, and Ix and Iy are moment of inertia about x and y-axis, which lie in the plane of the objects. So let's understand what this statement is actually saying. So let's draw an axis. So these three axes represent Ix, Iy, and Iz. So they are at the point where all the three coordinates lie. Now remember that this perpendicular axis theorem is applicable for the two-dimensional objects. Means it is not applicable for any three-dimensional objects. So we can say that x and y should be lying in the plane of the body. So plane of the body means what? Any objects that is lying as a planar body in x and y system. So if we can consider this, so let's suppose this is a point which is at a distance of x unit from this axis. So this is x unit from this axis, that is Ix, and y unit from this axis, that is Iy. So let dm be the mass of this object. Okay. So how can we represent in the form of x and y axis? Let's see. So we can calculate, according to the perpendicular axis theorem, we know that Iz is equal to Ix plus Iy. So here a small mass of dm can be represented in form of x as dix is equal to dm, which is the mass of the object, x square, because this is a distance of x from the x-axis. Okay. Then diy can be represented as dm times of y square. This is following the same rule of moment of inertia, that is I is equal to mr square. So diz, which is now the z-axis that is perpendicular to these two planes, can be represented as dm times of, if we say this being r distance, so this can be represented as dm times of r square. Got it? So when we write it, we can write this r square, which is actually the hypotenuse of this x square and y square, because you can see that this is forming a triangle. So r square can be represented as x square plus y square, right? So we can write this as in the form of dr square. So diz, which can be represented as diz, can be represented as dm r square. So further, if we want to write, we can put this r square as the value of x square and y square, and we can write it as diz is equal to dm times of x square plus y square. Got it? So we are integrating it to get the total value of the mass. Getting it? Then left hand side and right hand side. So we can get Iz is equal to dm x square, right? So dm x square is nothing but I times of x plus dm y square, which will be yielding I times of y. So Iz is equal to Ix plus Iy. We can represent it this, and thus we can prove that the perpendicular axis theorem is verified. Remember that with this axis, perpendicular axis theorem is not valid for Iy is equal to Ix plus Iz. This is wrong. And Ix equal to Iy plus Iz. This is also wrong. So these two is not valid because the planar axis that we are taking is Ix and Iy. So the object that is planar is lying on x and y plane, and z axis should be perpendicular to it. So the axis that is perpendicular should only be equating x and y axis here. So we can now say that this is the correct method to write Ix and Iy for the perpendicular axis theorem. Now we shall do it for different objects that we can have. So let's see how it is. It can be verified for ring, for disk, and all. Okay. So we can study this for a ring or for a disk. So what is the moment of inertia for a disk we can encounter? Just a second. So let's suppose you are drawing a disk. Okay. So let's highlight this. Disk has an inner part that we can. Okay. So inside part of the disk can be represented like with the red color. Okay. So these axes can be taken as like this. So we can represent this as Iz, Iy, Ix. So as we know that Iz is equal to Ix plus Iy. We also know that the moment of inertia of a disk for an axis passing through its center is mr square by 2. This we know from the previous class, where r is the radius of this disk. So applying this, we know that this is a symmetrical object, so we can say that Ix is equal to Iy. So which can be taken as, let's say, Ix. So it can be, by using the perpendicular axis theorem from here, we can say that Iz is equal to Ix plus Ix, which is nothing but 2Ix. So we can represent this as 2Ix is equal to mr square by 2, which will say that Ix is nothing but mr square by 4. So this is for an axis that is for the x direction. So by the help of the perpendicular axis, we can find the moment of inertia about an axis passing through diameter from its center of mass as mr square by 4. Next, we are going to find for a ring. So for a ring, we can take so same concept we can apply for ring also, and we can see that the axes that are perpendicular to the ring can be made like this. Okay, so we can represent this as same Iz, Iy, Ix. So for ring, we know that the moment of inertia about center of mass is what? It is mr square. So same if we want to find it for the x-axis, we will get that for the ring it would be Ix is equal to mr square by 2. Okay. So with the help of perpendicular axis theorem, we can find it for different shapes like sphere, cylinder, and everything. Let's solve a question now. A wire of length L and uniform mass density ρ is bent in the form of a circle. Find the moment of inertia about an axis as shown. So the figure would be like this. There would be this circular wire of length L, and The axis that we are going to find out is this one. So this is the axis that we are going to find the moment of inertia about. So it is given that the entire wire is bent in the form of length L and this density of this wire is rho. And it is bent in the form of a circle. So L is nothing but the 2 pi r. So we can take the radius of the wire as r, okay, from the center. And moment of inertia about the axis is shown. So this axis we have to find. So before that, we need to find the moment of inertia about its diameter. Means this one. First, we need to find the moment of inertia about this axis. Okay. How do we find this? We already know what is the moment of inertia about an axis that is passing through the center. That is Iz. This being the z-axis. And this we have to find. So how do we find this? We know that Iz is equal to Ix plus Iy by the perpendicular axis theorem. And we know that here we can apply that Ix is equal to Iy by symmetry as it's a circular object. So we can take it Ix as 2 times of Ix as mr square, right? Where r is the radius of this bent wire of the circle. So Ix can be represented by mr square by 2. So this is the moment of inertia about this axis. Okay. We want to find the moment of inertia about this axis. So how do we apply this theorem then? This was the perpendicular axis theorem that we have applied. And now we are going to apply the parallel axis theorem. We know that we have learned the parallel axis theorem in last class. We know that where I can be given that I means the moment of inertia of the axis can be given as the moment of inertia along the center of mass plus mr square. So here the center of mass is already been known, which is mr square by 2 for a ring, right? Okay. And we know that mr square is for this. So we can just write that I can be exactly found as this one as 3 times of mr square by 2. So this is what we have. And this is it. But here we don't have the data in the form of radius. We have instead L and rho. So to convert this in the form of L and rho. Because the options that are given are in the form of L and the density and the mass density. So we have to convert this and we have to find the answer. So this entire circle is actually situated of length L. And we can write this as L is equal to 2 pi r. So to get the value of r here, we can say that r is equal to L by 2 pi. So we can substitute r square as L square by 4 pi square, right? What else we needed? We needed the mass. Now we have to find the value for m in terms of density. So m can be represented as density is equal to mass times of, so linear density is equal to mass per unit length. So mass can be represented as rho density times of length. So now we can substitute in this part and find the value in terms of rho and L. So I can now be represented as 3 times of rho L times of r square, which is L square by 4 pi square divided by 2. So in turn, when you multiply this, it will become out as 3 rho L cube by 8 pi square. So let's see which option matches the answer. So 3 rho L cube by 8 pi square is matched by the C option. So answer C is the correct. So this is how we solve a question that is using both perpendicular and parallel axis theorem to find the moment of inertia. And the methods can be very easily understood by solving these kind of questions. And in general, for any question in rotation, we can apply both the concepts simultaneously and find the answer.